So anyways, the last bit of lecture one, I wanted to talk about electric dipole moments. So if you have a spin one particle and you couple it Dirac particle, sorry, we are having technical difficulty of setting up again. So if you have a spin one particle, a spin one half particle, or spin one particle, doesn't matter. The typical story that is a Dirac particle can couple to the magnetic moment, right? So you have a spin times the magnetic moment that is a part of your Hamiltonian that is invariant under parity and time reversal. If on the top of this interaction you have some small parameter added times the spin times the electric field, this spin times the electric field breaks parity and time reversal. Breaking of time reversal by the virtue of CPT theorem also means breaking of CP symmetry. So therefore, looking for this small parameter called electric dipole moment also is a test of CP symmetry. CP symmetry, as we discussed, is broken inside the standard model. So you expect at some level the electric dipole moments of particles to be observed, yet it hasn't been observed. And there are two sources of CP violation inside the standard model, which one is too high, it gives too large a prediction, and the other one is too small. Okay, so we have interaction that is observed for all protons, electrons, neutrons. The addition of this term would break parity and time reversal. So the idea was if you take Maxwell's equations and you apply parity or time reversal, that you have either both sides changing sign or staying the same. So the equations are actually invariant under these transformations. And the idea of Purcell and Ramsey was like, oh, we don't actually know the true theory behind strong interactions. So are we sure that it conserves parity? This is a very groundbreaking idea for the time. And they've done a first constraint on the neutron EDM, repurposing some neutron scattering data taken by Fermi. Since then, it was realized that this is a very, very profound test of CP, and it's been sort of a race to see a non-zero EDM. So this is done not only with neutrons, but this is the latest bound on the neutron EDM, but it's also done with atomic systems that has electrons and nuclei inside. So you probe a lot of CP violation associated with it. And there are, in the recent years, there's been, compared to this limit, there's been a factor of 400 improvement of constraint on electric dipole moment of the electron. If you think about it in sort of effective operator language, this would probably scale inversely proportional to some new physics scale. So factor of 400 improvement correspond to a factor of 20 improvement to the sensitivity of that scale, with a lot of things being fixed. And a factor of 20 improvement, this is roughly maybe commensurate with going from like Tevatron and previous colliders to the LHC. So this is a big progress achieved in the last decade. The experiments are still ongoing, and we have we have therefore I have to pay attention to this part of the story. So we have some sort of sources of CPU violation and maybe CKM CPU violation here if we talk about very well established sources of CPU violation. And in principle, it can introduce electric dipole moment. It can introduce semi-leptonic CPR operators or some operators in the hadronic sector. In the hadronic sector, however, there is an issue that in principle you have a dimension 4 operator inside the Stern model that you would like to throw away, but you can't. This is so-called theta term of the QCD. We can talk a lot about it, but perhaps next time. So the two sources of CPU violation inside the Stern model that we should know, of course, is the Kabiba-Kobayashi-Moscow phase that is very well measured in all the things that I said in the previous lecture. But it predicts the EDMs that are too small to be observable. Okay, how small we'll discuss in a second. And this is if your goal is to test the CKM paradigm, the EDMs are absolutely not the way to do it because you're not going to do it. And even if you do it, you'd be subjected to a lots of QCD uncertainties if it's a neutron EDM, right? But on the other hand, you can say, oh, well, I'm looking for beyond Stern model physics where a much larger effect can be observed. And therefore, the background, let's say, from the Stern model is small. So this is a gearing towards a discovery of new physics. However, there is another source of CPU violation inside the Stern model. And it's not seeing an EDM with that accuracy. It consists of setting a constraint on the parameter. So when I say that all terms of the Stern model have been established and measured, that except for this one, that is not. Okay? So interestingly, none of these two sources is strong enough to induce a dynamical emergence of the baryon predominance over anti-baryons in the early universe. And so BSM CPU violation is required. All right. So returning to this CKM, if you remember the answer for the delta F equals 2 amplitudes, it was suppressed by the square of the Kabiba angle, G Fermi squared, M charm squared. And if you calculate the EDM, you will find many of these suppression factors. Plus, there will be a suppression by 3 loops here. And the suppression by the external quark mass that is small, and by the parameter here of the invariant CP violation inside the CKM, which is 3 times 10⁻⁵. So this all together will amount into the neutron EDM to be less than 10⁻33 centimeters, and the limit, I remind you, is 10⁻26 centimeters, so it's far away. Now, one thing that I wanted to say is that for a long time it was believed that the situation with electron EDM is even more kind of pessimistic from the point of view of the CKM angle, and then last year we realized that that's not exactly the case. So the electron EDMs are not an actual measurement because nobody measures the electrons in isolation. They're all attached to inside an atom, right? As such, there are kind of two effects. On top of the electron EDM that is basically an EDM on the outside of the atom that participates in optical transitions. There is also this interaction of this electron with the nucleus, and if this is CP violating interaction, it induces the very same observables. So you don't measure the electron EDM in separation, but this experiments kind of quote the result in terms of the electron EDM. So what they do, in fact, it's quoted in terms of equivalent electron EDM, which is in fact a combination, linear combination of an actual EDM and this semi-leptonic operator. This semi-leptonic operator, the sensitivity to it is at the level of 10 to the minus 10, which underscores how sensitive these experiments are, because we dig inside the Fermi interaction by 10 orders of magnitude. Okay, yes. All right, okay. So the simplest situation would be that you would have a small background magnetic field that will create a spin precession. On top of this, you will have a very strong electric field that you will periodically flip in the direction, and you would see a shift of the frequency with respect to the relative direction of E dot B. Okay, so if you don't see it, you set the limit of the spin precession frequency, right? But this is evidently altering the Larmor precession of the spin, right? If this D is not zero in the presence of the electron field, electric field. So this is how it's done for neutrons, for example. With atoms and molecules, there's a whole bunch of other techniques that one can use, but the electric field is important, and much of the progress in recent years was achieved with molecules, because they can you can run these experiments at effectively smaller electric field, benefiting from the fact that the small electric field can lead to the orientation of the molecular axis, and which kind of enhances the electric field acting on the spin of a particle whose EDM you want to measure. That's a qualitative explanation. Now the thing that we have advanced recently is we understood how the equivalent electron EDM is sourced. So if you kind of go back to this diagram, this would be, and we take the CP violation from the CKM. The main effect is to induce semi-leptonic operators that then feed into electron EDM experiments. And the diagrams that are important is already encountered by us, electroweak penguin diagrams and strong penguins. So this is gives by far the largest result, and the equivalent EDM of the electron calculated this way is at the level of 10 to the minus 35 centimeters. So once you see lots of formulae in someone's presentation, it means that he or she reached their own work, right? And this is perhaps I should spare you with the details, but the idea is that this the calculation is actually indeed the electron EDM is going to be third order electroweak effect. And so the equivalent, let's do this semi-leptonic operator, CS operator, is proportional to G Fermi cubed, mass of the top squared. There is some loop factor. There is this 3 times 10 to the minus 5 invariant JCP from the from the CP violation of the CKM, and also there is some hadronic scale entering. So this is all calculable, and this I'm missing a slide, unfortunately. I notice, and then the result is proportional to 10 minus 35, which is 1,000 times larger than believed before. This is interesting, but it's still very small compared to the current limits that are at the level of 10 to minus 30. So there is quite a bit of progress to be made. Now, the last comment I wanted to make about the CP violation inside the Stern model is that there is a hidden parameter inside the QCD that violates parity and CP. So this is a tribute to Purcell and Ramsey, who thought, oh, we don't know the true theory of strong interaction, so we cannot say, right, whether this is the parity is respected or not. So some 30 years after their work, people have realized, oh, the true theory is a QCD, and by the way, there is a new parameter that can break CP. So this is a full derivative, however, from the gauge non-invariant operator, and you cannot throw it out because non-perturbative effects make this GG dual operator not innocuous, that you have to keep it in. And so if you go sort of towards a small theta angle and expand the energy of the vacuum, there is this formula which is quadratic with respect to the theta angle, and it has a plus sign, minus sign, never mind, QQ bar has a negative sign in it. Now and M star is this product of up and down masses. So this is good, right? If you have a quadratic term and the potential, you know that the things will slide down the potential and stay at the bottom. So the theta term should be zero. However, inside QCD, there is a super selection rule that this transition from one theta to another is prohibited. Okay, unless this theta is the dynamical field promoted to a dynamical field called the axion. If you don't do that, your theta is in principle arbitrary, and this induces the EDM about 10 orders of magnitude larger than what you observe, which introduces a fine-tuning problem why theta is so small. So there are some ways of addressing it. One sort of economical way would be requiring the mass of the upwork to be zero, but this is seemingly probably inconsistent with, most likely inconsistent with the hadronic spectra and the difference in the masses of light hadrons induced by non-zero quark masses. Now, you can have theta equals zero by construction. But then you need somehow a tight control over the theory, right? Theta is a dimension 4 operator, so in principle is sensitive to arbitrarily high scales without any suppression. Yes. Right. So if you have let me kind of discretize a theta or something like, oh, well, not necessarily, but say you have a theta with one value of the theta, and you take any gauge invariant operator, and then you should always deal with those, not with others. And theta 2 here, and this result is always going to be proportional to theta 1 minus theta 2. So therefore the two sectors with two different thetas do not talk. They correspond to two different physical theories, such as is somewhat similar to like coupling constant. What it means is that even though the energy here is dependent on the theta, this is energy, this is theta. If we put a particle here, a system here, a vacuum here at the side, it will not slide down because process of sliding down would have to involve talking between the jumps in theta, right? So if your all amplitudes are always going to be proportional to that, it means that you will be confined to that value of the theta. Any questions? Very well. So when we try to make theta equals to 0 by construction, we typically require parity or CP symmetry acting to very, very high scales. And this is a very tightly constrained scenario. And what's really defying our expectations of the decoupling is that you have to have control over almost arbitrarily high scales, right? We have always the decoupling idea built in our heads. Who cares what happens at the Planck scale, right? Except for some set of operators such as the Higgs mass, cosmological constant, and so on. And the theta, being a dimension 4 operator, is definitely in principle sensitive to all the sources of CP violation above. Once we introduce an axion, which I should admit my preferred solution to the strong solution to the strong CP problem, we reintroduce our normal way of thinking. Maybe there is like CP violation at the Planck scale, and maybe it renormalizes the theta term by order 1. Who cares? The axion will relax everything, including that to an observable value near 0. That's in the category you shoot and you forget, right? Except that they might come back to you or bite you in the sense that gravity, some people say, may violate Pechi-Quinn symmetry. But as Matthew said last time, this is what did you say? Above my pay grade or something like that. Very well. So this is all what I wanted to say in the review of the standard model. Overall, full consistency of the CKM paradigm in the quark sector with ever increasing precision. Not without hiccups, right? There's some tension in this and that decay, and we'll see. It very well may be that some of these tensions will develop into something new, right? If we go back to this early days of the neutrino problems, right? So there was experiments with chlorine turning argon in Ray Davis's experiment in the US in the late 60s, early 70s, that was undercounting the solar neutrinos by a factor of 2 or 3, right? So at that point you thought, okay, maybe astrophysicists calculated it wrong. Maybe Ray Davis misses some of the argon atoms that appear from his apparatus. But in fact, it later on matured into an actual idea of the neutrino oscillation, and it's indeed what's happening. So who knows, maybe we are at the very early start of that, and we will see how this problems, sound tension in B physics data develops into something, let's say, beautiful. I haven't, even though I contributed to some model building, I would not be pressed to call any of these models beautiful, although some people have their own ideas about beauty. Anyways, this we'll see. So far, I don't think the amount of evidence we have at hand necessitates us calling for new physics at this point. All right, neutrino physics is all right. The other things we discussed is that the results in the last decade were basically convincing measurements of the electroweak penguins. Before that, electroweak penguins appeared in one diagram only, and this was a real part of the long decay to mu plus, mu minus. Okay, so that's also the electroweak penguin, but this time around we see that this is the dominant source of BS to mu and K plus to pi plus nu bar and so on. The neutrino masses are not in the Stern model, but we have discussed how you can put the neutrino masses in using the seesaw framework or the Weinberg operator of dimension 5. Then Flavour diagonal CP violation is well motivated, and one way to probe it is with electric dipole moments. Here we have two sources. One is too small, CKM, doesn't induce much of an EDM. Even though we have found some enhancement for electron EDM, it's still not enough to be observed. And the vacuum QCD angle, it gives too much of a CP violation, if you like, perhaps implying an axiom. All right, this was my review of the Stern model. And so how much do I have time left? 1 hour. All right, this is probably more than enough. All right, so in lecture 2, we are going to discuss standard model corrected by effective high dimensional operators, and perhaps look into some well-motivated extensions of the standard model, right-handed neutrino and so-called inverse seesaw, multi-Higgs models, and supersymmetric models. Used to work on this quite a bit, but this was a long time ago. So when I was looking through my notes, thinking what to say, I was certain things were coming back to mind, but I might be rusty, so I apologize. And then we would talk also about probing the Higgs properties with the Flavour and EDMs and probing 100 TeV supersymmetry. So the subject of this lecture is studying the effective operators added to the Stern model. So that is if we are oblivious about these kind of models we have, right? If we know exactly what model we have, and every theorists probably have something like that, then we can insist that we can predict the coefficients, Wilson coefficients in front of these effective operators, and we have a clear idea. Or maybe the experimental anomalies would lead us to a certain values of these coefficients. All right, so let's talk about the effective operators. Currently, we have evidence for all standard model fields and all terms in the Lagrangian. We should say, but theta term, right? This is a small blemish here, right? In parentheses. But then the all neutrino oscillations can be in principle, the effects can be in principle described by dimension 5 operators. And we don't see any dimension 6 operators. Okay, so this is a very suggestive, consistent story, right? So there's definitely a standard model extended by the dimension 5 operators and neutrinos is very consistent. The only way I know where it breaks, it does not have enough dark matter, right? And then you would have to put some other particles in, and that we'll talk about that next time. tomorrow, that is. So we seeing dimension 5 operators, not seeing dimension 6 is kind of natural, right? Because this the higher the dimension of the operator, the more it can be suppressed. All right, but that's far from a definitive proof, and there could be hierarchies between the operators. But let's just have a look. The dimension 5 operator we have, as we just discussed, there was this type of operator that leads to a neutrino mass scaling with vacuum expectation value over 2 lambda. So here called the lambda 5, we equate it to some sort of a scale of the neutrino masses observed in the experiment. I interpret the atmospheric and the solar mass difference in terms of sort of a characteristic mass scale. Then we get to lambda 5 to as high as 10 to the 15 GeV. This corresponds to Yukawa couplings of order 1 and the right-handed neutrino masses at that scale. So exceedingly high scale. Another even higher scale, in principle, you can probe with the proton decay or nucleon decay in more general, where you have 4 fermion operators that connect, for example, down quark and the positron, right? Something that I guess I should put a bar here. And then this would lead to, for example, a proton decay to a positron and a pi 0 that in the environment such as super Kamiokande detector would correspond to a spectacular 3-ring event with the pi 0 giving two Cherenkov ring, and the third ring given by a positron, all reconstructing, although with some resolution, the proton mass. The limit on this is 10 to the 34 years. Do you know how to arrive to this 10 to the 34 years? How many protons are per gram of water, give or take? In 1 gram, yes. 10 to the 23, more like 10 to the 6 times 10 to the 23. This would be Avogadro number of protons, right? Or nucleons in general. Now, what is the volume of the, should say, fiducial volume of the super Kamiokande detector? 10 tons? Who else? Who has some other ideas? 20 kiloton. So this roughly corresponds to the total mass is 50 kiloton. This is if we are in the trivia business, this is 20 swimming pools, Olympic swimming pools. Okay. So, anyways, 10 kilotons is 10 to the 10 grams. So 10 to the 10 grams times 10 to the 24 particles per gram gives you 10 to the 34 particles. Now, if none of them decays in 1 year with the efficiency of that signal order 1, that's the limit you're going to get, right? And that's the limit they got, right? So in 20 swimming pools of Olympic size, no protons have decayed in 1 year, right? So it's something, right? And that's that limit. You can translate back to with some QCD uncertainties, but okay, let's sweep it under the rug and so on to the limit on the scale, and you get indeed very close to the grand unified scale. The problem with this experiment is how to improve it. There is no nifty tricks that you can play here to enhance the signal. You cannot induce the proton unless you have some monopoles to throw at it, right? But you don't, right? So this is the only way to go is to have a larger amount of water, right? And this is perhaps can be improved in sort of dense phototubes implemented somewhere in the ocean somewhere. Perhaps that's the way to go. Okay. Right. So if then there is other operators, and let's arrange them in terms of the symmetries they break, right? So here, like dimension 6 operator that I've written breaks baryon and lepton symmetry at the same time, leads to the proton decay. Now let's assume that the proton is stable, but let's introduce some new operators that break Flavour. Say convert 2 s quarks to two down quarks, and that would lead to the K0 bar mixing. So we have to compare this with the standard model answer for the box diagram that we have discussed, and that leads to the sort of 10 to the 6 to 10 to the 8 GeV sensitivity to the scale lambda, depending on what type of operator you have and whether it has a real or imaginary part, because the imaginary part would contribute to epsilon sub k, which is even tighter measured than delta mk. Now, if you have delta f equals 1 operators, so one of the possibilities is indeed that you have some operators that induce k long decay to e plus e minus. This is also like branchings at the level of 10 minus 10, and you can reach the scales of 10 to the 6 times the hadronic scale. If you have you can have delta f equals 1 operators in the lepton sector, and that would, for example, correspond to muon decay to an electron and a photon. This is not seen in the MEG experiment, and neither is it seen in Muto 3E, or well, a previous reincarnation of Muto 3E, or muon conversion to an electron, and that is roughly corresponding to the scale of 10 to the 6 GeV. Some of the counting here is a little funny because when you have F mu, more likely than not, that this is induced by the loop effect. So in some realistic models, you have to supply it with the loop suppression factor unless you have run into some strong interactions. Other interactions here could, in principle, emerge at the tree level with the new particles exchanging. All right, where are we? So if we continue, there could be flavor conserving CP and chirality odd operators such as the electron EDM. So I put here E left, E right, but I've been, explaining many times, or trying to explain many times, that this is not SU2 cross U1 invariant operator. So therefore, I introduced a Higgs web, or I could introduce a full Higgs doublet here and put left-handed doublet as well. So this scale, comparing it to 10 to the minus 30 centimeters gives really an enormous scale here as well. I should check that number. I was doing it last night, and I might have introduced a mistake. I got to check. Now, there could be operators that conserve flavor but still break chirality. For example, if you write QLDR times ERLL operator, okay? So this is An operator that is inside the standard model would always appear with a super tiny coefficient. Why? Because any conversion of the right-handed fermion to a left-handed fermion costs you a Yukawa coupling inside the standard model. A Yukawa coupling for an electron is a tiny number, 10 to minus 6 or so, right? So this, if you write it something like that without a Yukawa proportional to Yukawa coupling, this is what we would call chirality violation, and it would lead to the new physics amplitude relative to the standard model amplitude that would be enhanced in the pion decay by m pi over me, because the standard model decay is suppressed by me. This is checked to a few percent level that would still correspond to the sensitivity to the high dimensional operators at the level of 20 TeV or so. And it can be further improved in upcoming PSI experiments. This is just to say that when we have this 20 GeV, 10 to the 10 GeV, 10 to the 5 GeV, this is, if that's the scale of new physics, you have no chance with, say, colliders reaching that scale. However, there are lots of operators that, let's say, all these previous symmetries are fulfilled, and then you have some operators that connect quarks and leptons and so on. Then the degree at which you can apply low energy physics observables to it is somewhat diminished. Like you can try to do contributions, modifications to atomic parity violation or parity violating scattering of electrons, but this is sensitive to at best 1 TeV scale. Well, while at the LHC you can be sensitive to a few TeV or so. So that's like a quick look at the operators, and of course this scales widely different. So for the rest of this talk, I will assume that the baryon number is conserved and so on, and we talk about the flavor violation. So let's in principle formulate a couple of approaches. Flavor anarchy and minimal flavor violation. So if you have flavor anarchy, is basically I will write an operator that contains 4 different flavors, and let's say everyone talks to everyone else at once, right? So we will have some sort of, it's kind of similar to Sagdev E. Kitaev Lagrangian. Anyways, all these 4 fermions talk to each other, and in principle, these are order 1 coefficients. Then the best constraints will actually come from delta M sub k and epsilon sub k, because these are the most tightly constrained parameters in the flavor physics, right? These are the smallest parameters. And this would be a framework that would be very hard to improve with the flavor physics. Why? Because of what we discussed last time, that this is gonna be a measurement of the standard model of delta M k and epsilon sub k versus the standard model prediction. Whatever, and you have to subtract whatever is left is for new physics. So if you don't have a full control over what you're subtracting, you don't have a very tight constraint on new physics. Well, no ways of improving it unless you improve the accuracy for the matrix elements. So everything will depend in the future of how well we can calculate this on say on the lattice. And a progress has been made, but it's not being, like orders of magnitude gain and improvement. Now, the opposite end, there is a so-called minimal flavor violation framework. Now, this basically tells you that all possible sources of flavor transitions come from YU and YD, and standard model reparameterization invariance is preserved. So in particular, for example, the right-handed CKM angles do not appear, right? Then when you write an operator that would be of this type, there should be an index here, then you would describe it in terms of possible structures that involve so there is no index now. The indices are converted using the Yukawa matrices, and in particular, the right-handed fields will always come with the corresponding Yukawa matrices multiplying them. So to go from the right-handed downward, you cannot have top mass, for example, contributing. It will be a mass of the down quark and so on. And so in principle, I should be writing YU dagger, and I always get confused where the dagger goes. But I can cheat myself out of this because the reparameterization invariance is preserved. So therefore, I can rotate the right-handed fields to such way that all my Yukawas are Hermitian matrices, and then I don't have to worry about where I put the dagger, right? So that's my way of cheating. So why square times YD by the term that yeah, it's YD cube. Yes. Okay. Yeah. I was just multiplying it in LaTeX, right? So the point here is that all your Wilson coefficients are no longer matrices, but the complex numbers A, B, and so on. And the only thing that in this approach that I cannot do here in this expression is to replace YU squared and YD. If I put it that way around, this will create a physical right-handed CKM matrix, which is not the case. Okay.
Why you can only choose a basic approach to remissions?
Oh. Well, I just said that the Snare model reparameterization invariance of this is valid, right? So when we go back to this arbitrary D quark matrix, I can multiply it by a certain transformation from the right, and I can put it to the Hermitian state this way. I believe there is a theorem that you can prove that this is always possible. So using the rotation from one side, you can put any matrix to a Hermitian matrix. I believe we can prove it if we stop for a second. But the point is that this is a framework parameterized by A and B and so on complex numbers that don't have flavor indices, and this is a framework that naturally emphasizes, for example, effects in B physics relative to, I mean, like chaos. No longer looking outright winners here in this framework. The B physics is equally or more informative, and another thing where it also emphasizes the collider constraints. All right. So this is all what I wanted to say about the operators. Now I would like to walk over certain perhaps models, and we discuss a little bit of that. So what is the most motivated particle as an extension of the Stern model? Everyone should have their own favorites. So some people would say axion, some other people would say right-handed neutrino, right? So there's very, very solid grounds for the both points of view. Now let's talk of this, and towards the end of the last lecture, I was arguing that if we take the minimal model where we just put this NR, for example, as a Dirac particle or a very heavy fermion, giving the Majorana mass to right-handed neutrinos, the observable effects on lepton-Flavour violation is very small. But this may not necessarily be the case. Consider that there is NR and NL forming basically a heavy Dirac neutrino. So, and let's have one of these guys also mixing up with LHNR. Okay. So when you do that, you can ask the question: would the neutrino get mass, the active neutrinos? And the answer is no, because the Dirac neutrino cannot change the direction of the arrow. If we have new L coming in, there is insertion of the Higgs wave. There is another cross with insertion of the Higgs wave, and here is the propagator of the right-handed neutrino, Dirac neutrino, that will have p squared minus mn squared. So this whole thing will correspond to 1 over mn squared, nu bar kind of p slash nu. And this is a renormalization of the wave function, but not the mass. Okay, so I'm allowed in principle to use the equations of motion here, and this will just go to zero, goes to zero on the equations of motion. If you mix the standard model Dirac neutrino, or the left-handed neutrino, with a heavy Dirac sterile neutrino, you're not getting any mass. Okay. Now consider now that there is a small Majorana mass perturbation. Let's call it mu. In this case, the left-handed neutrino can go to the right-handed neutrino propagator. Then there is this V parameter. Then there is a mu insertion. It continues. Then there is a V insertion, and the left-handed neutrino. So this, the direction of arrow changes. So this creates a Majorana neutrino mass for active species that is going to be proportional to Yukawa coupling squared, V squared, mu parameter, divided. Now I have two propagators of this heavy neutrino mass, and this will create mn squared in the denominator. All right, why do I do that? I introduced a small parameter mu that is, in principle, can account for the neutrino smallness of the neutrino masses, and I can increase the size of the y parameter here, the Yukawa coupling of the neutrino, right? If before in the seesaw mechanism, it was always proportional to the active neutrino mass, and in some sense. So now I by introducing this mu parameter, I decouple the neutrino mass generation from the mixing with the sterile neutrinos or from the Yukawa couplings. So this is not a crazy framework, because this basically corresponds to a small violation of the lepton number in the heavy neutrino sector. It can be made natural, if you like. The consequence of this would be the large enhancement of the lepton-Flavour violating amplitudes, in principle. So suppose we consider some heavy neutrinos at the electroweak scale. Okay. So if we consider heavy neutrinos at the electroweak scale, then the prediction for this E mu amplitude will be proportional to the Yukawa couplings that stand here. They're different, but let's forget about that. There is a proportionality to the mass of the heavy fermion here, and inversely proportional to a square of the sterile neutrino. Now, in the normal seesaw, the Yukawa coupling squared is going to be proportional to the mass of the active neutrino times the electroweak wave that I have basically, divided by electroweak wave. The what do I do here? No, sorry. In normal seesaw, we have the relation between the active neutrino mass to be Yukawa coupling squared V squared over the mass of the neutrino. So the Yukawa coupling, therefore, squared will be proportional to the active neutrino mass times this Mn divided by V squared. And since I took them on the same order of magnitude, it's going to be M nu over V, and this is going to be sort of 10 to the minus 12 kind of value, because this is what this parameter is. Now, inside this inverse seesaw, you don't have this parameter, and this could be potentially order 1 for inverse seesaw. So this is therefore this amplitudes, Lepton-Flavour violation, would be possibly much enhanced in the inverse seesaw framework, and this would correspond to basically Lepton-Flavour violating experiments probing next to minimal neutrino mass models. Questions here? All right. Another well-motivated extension of the standard model is the basically multi-Higgs. So what I did, I copied the standard model Higgs term, and then I put phi 1, phi 2, and then I have to put labels 1, 1, 2, 2. So in principle, now we have 4 Yukawa matrices, and there's a lot more free parameters, and they may not be diagonalizable at the same time. If that is not the case, then we would expect that some of the additional Higgses would introduce the flavor changing neutral currents, because once you added the second Higgs doublet, you have 4 more Higgses, 2 charged, scalar and pseudoscalar, and then there is no reason for this flavor changing neutral currents to exist, not to exist at the tree level. In a decoupling limit, when one Higgs doublet is standard model like and the other Higgses are heavy, it is the heavy Higgses that will have bad flavor properties. Having said that, one could build 2 Higgs doublet models without flavor changing neutral currents. So Yukawa matrices could be self-similar, or could be diagonalizable at the same time. And one set of Higgses may not couple to fermions altogether, or like it happens in supersymmetry, up and down quarks get masses from their own Higgs doublets. And in that case, basically the choice of the additional matrices is 0. In this case, doublet 1 can be called HD and doublet 2 as HU. This is standard for anyone who studies supersymmetry, and I don't know, Could you show me by hands who have studied supersymmetry phenomenology by okay, so all the old guards have studied it, and not the new generation. There you go. Very good. So just to give you an example, what it can do, let's just discuss very briefly somewhat more restrictive framework when we unify this theory that we have written into some left-right symmetric theory. This is a very popular framework that sort of restores the parity above a certain scale. If you do that, you have to gauge the right-handed fields as well under its own SU2. And you have to unify the Higgses into what's called a bidoublet. In this case, basically what you have, not 4 Yukawa matrices, but 2 Yukawa matrices with the following identification. A Yukawa up quark matrix for the first doublet is equated to the Yukawa matrix of the down quark for the second doublet, and so on. The interesting part of this story is that if you insist on left-right symmetry, which is often the case in these models, the right-handed CKM becomes physical, and it's equal to the left-handed CKM. So this and the Yukawa matrices are by definition Hermitian. In that case, you get the very. This is not much emphasized, but this is true. That in that case, you have a very strong 3-level flavor-changing neutral currents that are mediated by phi2 particle, and we will assume that phi1 is the standard model Higgs-like particle. So what happens in this case is that the left-handed and right-handed down quarks are connected to a phi2 boson by the matrix YU. This never happens inside the standard model, and you can rewrite it in a diagonal basis. So you get up quark diagonal Yukawa matrix, and up quark diagonal Yukawa matrix contains the top quark Yukawa, which is numerically close to 1, and sandwiched between the delta CKMs. So this introduces at the 3 level the operator that flips flavor strangeness by 2 units. And if you consider the corrections to epsilon sub k parameter, you get the shift on the order of observed, 10 minus 3, times the mass of inverse mass of the phi2 particle, phi20, in units of 100 TeV. So this underscores how powerful the 3-level flavor changing is in the left-right models. And when I hear left-right models, I immediately think about this bounds, and the limits on the right-handed scale in that case are very high. And this is a consequence of 3-level flavor changing. All right, so I have a few slides on supersymmetry. This is as I missed Matthew's talks on Monday, but I'm pretty sure he has mentioned the sort of taming of the gauge hierarchy problem by canceling the top loops against scalar colored top loops and so on. So it's softening UV behavior of the scalar masses, including the Higgs mass. And unfortunately, at a low energy scale, it has 100 or so, a little bit more new parameters, even if you discard various flavor transitions, I believe. So this is the supersymmetry arrives when we go over and above this mass scale, because this corresponds to a soft, so-called soft breaking of supersymmetry. So indeed, it is of utmost importance what the masses of these particles are. If we 1 GeV, we would have been already in a very supersymmetric situation at the high energy colliders. Unfortunately, the result for the Higgs mass coming out of 125 implies a very heavy SUSY partner masses. Now, here is the thing. If you, I'm an old person, so I've been around. So when the lab ended, there was a constraint on the Higgs mass at 114 GeV or so. So if you talk to a SUSY theorist and you ask, what is your prediction for the Higgs mass that the LHC should see? And they would say 114.5 GeV. Okay, maybe 115, right? So there's, in other words, the thinking was that the lower the Higgs mass is, the less of the radiative correction from the stop sector you need, the lower the scale of the superpartners is, and consequently there is a less of fine tuning in the Higgs parameters that you need to use. So 125 really implies quite a bit of heaviness to the superpartners, and I would say having a Higgs measured at 125 and not seeing the superpartners is kind of mutually consistent things. I don't know if the SUSY experts can correct me. All right. So what does the supersymmetry do for the flavor? Remember that let's go to the framework where the up, down Yukawa matrices are all diagonalized, but then you have new particles, scalar partners of quarks, and in principle, the scalar particles can have don't have to be flavor diagonal in the same basis where the quarks are diagonal. So in particular, you can go from S quark to down quark via a superpartner propagator that would have flavor mixing built in it. So if you just look at how this diagram scales, it will pick up some gauge couplings, for example, alpha S squared, and it will be proportional to the mass of sort of flavor flipping mass of diagonal mass squared, weighted by the mass scale of the superpartners. So this is compared to the standard model calculation of the delta F equals 2 diagram that is very, very suppressed. So when we think about the TeV scale supersymmetry, that implies that the off-diagonal mass entries in the quark matrix are much smaller than the diagonal masses. However, if the Higgs results put the SUSY partner masses at 100 TeV, this would not require excessive fine-tuning because you would have like 100 TeV squared in the denominator here, and so a few sort of 10% kind of alignment would be totally okay with lots of constraints. With all the constraints, in fact. This is not the solution to the so-called SUSY CP flavor we had hoped for, right? Because you'd rather have a TeV scale SUSY, but well, that's where we are. So I would like to say that in principle, the SUSY models have can have a flavor blind, minimal flavor violation framework in it, and so there will be a large alignment of the quark masses with the quark masses as well. In principle, this is possible. What I like about it is that superpartner masses can be, say the supersymmetry is broken at a very high scale, and then the superpartner masses are propagated down to the weak scale or whatever 100 TeV scale where they sit using the relevant renormalization group equations. So In this process, you might be evolving particles from a scale of 10 to the 16 GeV all the way to a TeV. So in principle, you have an access to very, very heavy particles through the renormalization group equation. So for example, imagine that there is indeed there's some scale M associated, for example, with right-handed neutrino masses that can be as high as 10 to the 15 GeV, in which case the Yukawa couplings for these neutrinos would have to be order 1 if we're thinking about the seesaw giving the active neutrino masses. Then the right-handed, the quark masses, besides the sort of flavor conserving part, will also develop a part that is going to be proportional to this Yukawa couplings, and the logarithm, the masses of right-handed neutrinos will enter in the logarithm, and this happens because the theory will have a piece of the RG equations that is consistent with the running with the light above the right-handed neutrino mass. And so this insertion can be of a considerable, can have considerable off-diagonal terms, and this would lead to the considerable enhancement of mu to E conversion via the SUSY diagram with Slepton and Gaigino, much larger than otherwise in non-supersymmetric theory. So this is very important in supersymmetry, that fermion mass matrix can serve some sort of a recording box for the very high energy behavior of the theory. When I said that the structure of the Yukawas inside the supersymmetry is very similar to the standard model, that is true that there is no flavor changing neutral currents at tree level. However, there is still a considerable degree of freedom because of the fact that we don't know how the electroweak wave it breaks down between the two Higgs waves. Okay, there are two Higgs waves. The square of them enters in the MW squared, and that's fixed, and this is correspond to the V squared. But the ratio of them is not fixed, and it's in 2 Higgs doublet literature, it's called tan beta. It's a free parameter. It's very problematic to have tan beta much less than 1, and very easy to have tan beta much larger than 1. Why is that? If tan beta is much larger, tan beta is much less than 1, that means that the Higgs of up quark is much less than the V. Okay. If it's much less than the V, to ensure that the top quark mass weighs 175, I have to correspondingly enhance the top quark Yukawa coupling. The top quark Yukawa coupling is 1, right? So if I say the tan beta is 0.01, then the top quark Yukawa coupling is 100. It's not very useful, and it's actually will contradict directly to observation. On the other hand, the bottom quark is very light, right? So we don't know if the bottom quark is the product of 246 GeV kind of times the standard model Yukawa coupling of the bottom quark, or it's maybe bottom quark is order 1, but the corresponding wave of the down quark Higgs is small. This is a situation of that is perhaps not very poetically is called large tan beta in SUSY. Okay, so this leads to various enhancements in the flavor changing couplings and idioms. So if you consider, for example, an exchange by left-handed and the right-handed sort of mixed selectron scalar lepton propagator and super partner of a photon, that in SUSY models, this is proportional to mass of the electron times tan beta. So therefore, the left-right transition in this models can be enhanced by a factor up to 100. So this is when we say that left-to-right transition costs you a Yukawa coupling. In the SUSY models, you're not really know what the Yukawa couplings really are in the down quark sector. Okay, so there could be a factor of 100 enhancement of left to right transition. This also comes very handy if you want to fit the existing discrepancy. Let's say there is a discrepancy in G-2 measurement of the muon with the SUSY diagram, then a large tan beta will enhance all SUSY contributions. Also the loop effects enhance B to S to heavy Higgs vertices, flavor changing vertices at the loop level. S wave function can go to a B wave function, and the result is that the corresponding diagram is enhanced is suppressed by a loop factor but enhanced by tan beta. So if you count for example, BS mu amplitudes in this business, you will find that it is enhanced compared to naive to tan beta equals 1 limit by tan beta cube, and this leads to had led to some big hopes that B to S mu would be much enhanced due to the supersymmetry corrections, and that has not worked out. So you can just set limits on these theories, and that's it. Now, probably I'm going to skip this effective operators in SUSY. The idea is that when you have a supersymmetric models, the counting of the effective operators is slightly different because on top of the fermions, you have lots of scalars. So if you put 2 fermions, 2 scalars that correspond to dimension 5 operator and 1 over lambda to proportionality rather than 1 over lambda squared. When you integrate out squarks or leptons, what you had the 1 over lambda squared inside the Stern model would have to be identified with this parameter proportional to the inverse squark mass. All right, so in the remaining 10 minutes, I'm going to mention something about the Higgs properties, and none of these things about the 2 Higgs doublet model has been discovered at LHC, but the 1 Higgs we have discovered, right? And it's 125. Thank you very much. This is the plot I've already shown. This is the 4-lepton signal of the Higgs, just for illustration. And then the interesting question, what do we know about the Higgs couplings from low energy operators, including Flavour and CP violation in EDMs? One could have, for example, high dimensional operators that connect top quark with the Higgs. If there is a phase to this operator, you get the CP violating coupling of the Higgs to the top quark. That will kind of induce an EDM due to the closed top loop and the gamma, or a gluon instead of a gamma. And this is, for example, an electron. Or they can be effective operators, dimension 6, CP odd and CP even for the coupling of the Higgs to photons. Now, the interesting part of the story is that the Stern model typically contains CP even operators, right? Because the CP violation inside the Stern model is such a rare thing, right? And it involves all this generation, so it's suppressed in the Higgs physics. So CP even and CP odd operators would not much interfere, okay? So if you have, for example, this T I gamma 5 T times Higgs operator, will this increase or decrease the Higgs production? It will increase the Higgs production, because to decrease the Higgs production, you would need some destructive interference with the existing amplitude. Because we add some amplitude and it adds in quadrature, it will only increase it, right? Likewise, if we have CP violating coupling of the Higgs, so this gives Higgs to F dual kind of operator, then will it increase or decrease the branching of the Higgs decaying to gamma gamma? Again, it will only increase it because it doesn't interfere with the Stern model, so it leads to the increase. So yeah, when at some point people have speculated that maybe there is a signature of CP violation inside the Higgs operator, because at the very early stages of the Higgs discovery, it looked a little larger than the Stern model prediction. Regardless, you can place the limit on the Higgs gamma gamma CP violating coupling from the EDMs. So this is an effective operator that I plug in here, and I dress it with this is a Higgs, and this is a gamma, and this is a gamma. And you can easily calculate this operator, what we calculate is operator mixing, right? So I had a Higgs gamma, and then I recalculated on the electron EDM. So if you calculate it and you plug in the existing bounds on the electron EDM, the change in the Higgs to gamma gamma rate due to the maximum permissible CP violating part is super small, 10⁻⁶. That is to say that the low energy experiments are far better probes in most of the CP violating signatures. All right, so don't have much time to talk about this business, but in principle, you can have muon talking to electron via the Higgs, sort of a high dimensional operator that will induce this type of decays, but it will also induce mu to E transitions due to a Higgs exchange with the nucleus, as well as Higgs loop giving you basically mu to E gamma. So typically the sensitivity to this operators are better from low energy, with the exception of Higgs decaying to tau mu, where the tau constraints are not that strong. Now, what can we say about the supersymmetry at the super heavy scale? And the super heavy scale here, I'm going to take sort of this scale, which corresponds to 10 to 100 TeV, and that's where very much the super partners like to live, unfortunately, which is outside for the LHC reach, and perhaps and not clear if it's inside the future high energy colliders either, right? Okay, let's put it this way. So the flavor in this case can be a little bit relaxed. Remember, I said that the squark mass matrices have to be aligned with, but this was referring to a TeV scale. If you push everything to 100 TeV, then a bit of a flavor anarchy would not do you any harm. Okay. If you don't have a flavor, then how would you probe it, right? Is a biphysics would be a very tough proposition, because this is typically inducing way too small amplitudes for the biphysics. Kaon physics may be, but again, remember, to improve the Kaon bounds, you would have to improve the QCD, which is an exceedingly difficult proposition. What you can do is to perhaps probe the scales with electron EDMs and quark EDMs and so on. And why the flavor anarchy works? Because remember with this earlier, I had that diagram, it's over here. That was proportional to the mass of the electron in a sort of a, this is a flavor aligned framework. If you don't have a flavor alignment, but a flavor anarchy, you have basically maybe instead of ME, you have m tau times this angles of mixing in along this lepton line, and this is not guaranteedly small. So this same principle, you can get m tau over me enhancement, and of course for the up quark this could be a dramatic enhancement. You can put something, I don't know, mixing angle of 0.1, but then the top quark is 5 orders of magnitude or 6 orders of magnitude heavier than up quark. So in principle, the EDMs are not hopeless. You can estimate just to see what the size of this is. I'm very happy to say that we did this in 2013 with already the numbers that will look suggestive. 10 to minus 29, I remind you that these EDM constraints so far surpassed 10 to minus 29. They're currently sitting at 4 times 10 to minus 30. So this is normalized here at a scale of 100 TeV. And there is this parameter theta 1,3 squared times the gaugino mass in the units of 300 GeV. So this EDMs are perhaps could be discovered. Now here is a catch. You can of course if it's discovered and confirmed, the people who would see it would be, of course, receiving in due term a Nobel Prize and so on. But identifying where these EDMs are coming from would be exceedingly difficult because they will come from the scales of 100 TeV, and you would have to be in a very tough bind to see that. However, there is room for, in this sort of mini split scenario, for the gauginos to be lighter, and then they can be perhaps seen. All right, so I reached my conclusions. So the standard model extended by higher dimensional operators in the line of thinking that heavy states are being integrated out is a very robust framework consistent with data. Sensitivity to different operators depends on what symmetry you have violated, with the baryon and lepton breaking, giving you a proton decay, giving you the strongest constraints, reaching almost all the way to the grand unified scale of 10 to the 16 GeV. This is the perhaps the most important measurements at the low energy is the stability of the proton. Let's face it, right? Now, in Flavour, the strongest bounds come from the delta F equals 2 operators that lead to the mixing of K, D, B mesons, chems, and epsilon sub K being the most important parameters. And and this is very effective for constraining flavor anarchy, but in the minimal flavor violation framework, this is avoided. Okay. Now we went over several models, and I argued that models with the inverse seesaw are very well fit for enhancing lepton flavor violation, and this is the models where you uncouple the neutrino mass from the Yukawa couplings. So this is important. The smallness of the neutrino mass do not imply the smallness of the Yukawa coupling, even for the weak scale right-handed neutrino mass. Put it this way. In the two Higgs doublet model, this is a very tough, vast area to overview, but in principle, you should keep in mind that there could be flavor changing neutral currents. In left-right symmetric models, they take like the worst possible shape ever, and so this pushes the right-handed scale in my thinking to 100 TV level. In supersymmetry, the three-level flavor changing is avoided, but it's reintroduced in some versions. So, for example, large stunt beta gives large corrections to heavy Higgs coupling to flavor changing along the say B to S transitions. And the last things I said, that the Higgs boson properties can be constrained from low energy experiments. In particular, we can constrain CP-odd operators of the Higgs using the electron dipole moment. But not all. For example, tau mu Higgs is not really well constrained at low energy. And the final point that I have made is that electric dipole moments are perhaps the best hope for currently seeing indirectly the effect of supersymmetry at 100 TeV. I'm not a strong believer in the supersymmetry, but I still find it is to be a somewhat appealing framework because it solves at least the big part of the hierarchy problem from 100 TeV all the way to the unification, but it requires now somewhat tuned cancellation in the Higgs sector. Now, Matthew told you like 1% cancellation is making him uncomfortable, which is the thing about the fine-tuning is almost always about your feelings, right? Let's finish at that. Thank you.